Hello everyone, welcome to the video lecture series of the subject name VLSI Technology with the subject code KEC053 as per the AKTU syllabus scheme. So we have already covered the crystal structure. We have seen the crystal defects, what are the defects which are present in crystal structure, how the wafer is made, how the oxidation is done, and with the help of photolithography we have created some windows, and over that windows in the last lecture we have diffused some of the impurities, right. So after impurity deposition, when your final devices are fabricated, the last step is the metallization and the packaging. So today's lecture is dedicated to the metallization part, right. So in this this is the 5th unit of the syllabus, and in this chapter we are going to study the metallization applications, metallization choices, what are the metals which are available, and out of those metals, which metals we are going to prefer. Physical vapor deposition is one process for the metallization. Then we can have the vacuum deposition, sputtering can also be used to deposit the metal lines over the components. And then second half of the unit is dedicated to the packaging. Your packaging is done so that your device can be work with the external environment. Then what are the packaging types? Packaging design consideration, VLSI assembly technology, package fabrication technology, and CMOS fabrication steps. Finally, we are going to study what are the steps required for the CMOS fabrication, right. Now suppose you have this wafer. Suppose you have this wafer and we have created, this is the complete wafer, and over that we have created some sub-circuits. Some sub-circuits are there, and each circuit will have millions of components. Millions of components will be there, and each chip will be taken from this complete wafer, and then it is placed inside one IC. Then one IC will be fabricated and it will be packed in this way, right. So when you have millions and billions of components over this small wafer, we have to make some VDD connections, right, ground connections, and sometimes clock connections. If you are designing any digital circuit, sequential circuit, we need to provide these signals, right. And over that we have to supply some input, some output will be checked, right. And over that we also must have some interconnects. So all these connections are done with the help of metallization. So here this is the global interconnect which is provided throughout the circuit. Here we have the contacts, okay, so some small contacts, right. So this way the metallization is done, and it is very surprising that over only the 35% to 40% is dedicated for the circuits only, and rest 65% is used, area is used for the metallization. Now because the number of metal lines are increased in VLSI technology, so we are now working with the 7 to 9 metal lines to have the complete metallization of one IC. So what basically a metallization is, a number of conductors such as copper, aluminum, tungsten, etc. are used for the fabrication of semiconductor devices. Metals with high conductivity is widely used for the interconnections, which forms the microelectronic circuit. This metallization is a process of adding a layer of metals on the surface of the wafer, right. And the metals such as copper, aluminum are good conductors, and they are widely used to make the conducting lines to transport the electrical power and signal. Miniature metal lines connect millions and billions of transistors on the surface of the semiconductor substrate. So the conducting film provide the electrical interconnections. They are used to provide the electrical interconnections among the devices, as well as they are used to connect them to the outside world, right? So we can see in this figure, this is your simple MOSFET, NMOS, right? It is then we have this foundry diagram, fabrication diagram. We have this source, which is source and drain regions, which are done with the help of diffusion or ion implantation. Right, this gate material is deposited with the help of deposition. This is the oxide layer, which is done with the help of oxidation, right? These windows are created with the help of photolithography, right? So to complete this circuit, when we need to connect this circuit to the signals, we must have some metal contacts, right? So here you can see that we have this metal contact. P glass is used, thick oxide is used to passivate the device from another device. Here we have the metal lines, gate metal lines, and so on. So the primary metallization application can be divided into three categories. It can be used for the gate contacts and interconnections. The polysilicon and silicide are frequently used in the gate as a gate material and interconnects in the PMOS devices. Aluminium and copper are the metal choices which are used as a contact and second level interconnection to the outside world. And multi-layer structure involve a diffusion barrier which is used, and for this we use titanium, platinum, gold, titanium, palladium. Gold is used for the to provide the reliable connection to the external components. So it is important to reduce the resistance of the interconnection lines, since the integrated device circuit speed is closely related with the RC constant time. So which is proportional to the resistivity of the conductor. It is used to form the metal lines. So although the copper has the lower resistivity than the aluminium, but the technical difficulties such as adhesion, diffusion problem, and difficulties with the dry etching, etc., have hampered the copper application in the microelectronics. So your aluminium is used as a metallization for the metallization purpose since 1960 and 1970s. So pure aluminium or aluminium silicon alloy were used as a metal interconnects material. So, and by 1980, when device dimensions are decreased, one layer of metal interconnects was no longer enough to route all the transistors and multi-layer interconnections, because we are using millions and billions of transistors. So only a single layer of metal line is not sufficient. So we increase the metal lines. So to increase the pack density, there must be near vertical contact and vias and holes which are too narrow for physical vapor deposition of PVD of aluminium alloy to fill the wire without voids. So thus tungsten become widely used material to fill the contacts and via holes to serve as a plug, which is used as a connect to different metal lines. Then titanium and titanium nitride barrier adhesion layers are deposited before tungsten deposition to prevent the tungsten diffusion and peeling. This figure state here we can see that we have this tungsten deposition, right? We have this tungsten or tungsten nitride deposition or tungsten silicide deposition is there. This is done so that your when your final metallization is done, those metals should not deploy in the substrate. So that is why we use these materials as a plugs also. Then we have some of the areas where your metal lines can be used for gate and interconnects and contacts. We can use polysilicon, silicide, nitrides, copper, refractory metals, aluminium, and the combination of these metals. Then for the diffusion barrier, we must use some titanium nitride, Ta, titanium nitride, tungsten alloy, titanium tungsten alloy, and some silicides we can use. For the top level metallization, aluminum and copper are preferred, and for the selectively formed metallization on silicon only, some silicide, tungsten, aluminum, copper metal lines are used. So, aluminum on silicon or silicide, it can lead to some metallurgical interaction. So, annealing of aluminum on silicon, it will be done at 450 degrees C, which will cause dissolution of aluminum into the silicon, into the metal, and lead to a pit formation. So, if this prevention is deep, this penetration is deep, the contact and junction failure can be there. So, a useful solution is to dope the aluminum with approximate 1 weight percentage silicon. This serves to reduce the diffusion of silicon from the underlying substrate. So, however, the problem is not totally circumvented if the contact is fabricated on the N-type silicon, because the excess amount of silicon present in the aluminum can be used, and on cooling it will precipitate in the contact. So, this can lead to non-ohmic contact to N-type silicon, because the crystallized silicon precipitates contain aluminum which is of P-type dopant. So, in order to solve the problem, a diffusion barrier such as titanium nitride is applied between. So, this titanium nitride is applied between the aluminum metallization and the silicon substrate. So, we have seen in the previous diagram also. So, before the metallization is done, we deposit the layer of titanium or titanium nitride, which is used to prevent the aluminum penetration in the silicon substrate. So, generally the thickness of this in the order of 50 to 100 nanometer is sufficient for the application. Next problem is the electromigration, which causes considerable material transport in the metals, which occurs because of the enhanced and directional mobility of the atoms under the influence of electric field. So, then electromigration in aluminum is known to result in voids, which are manifested by the discontinuities in the metallization layers. So, and these will be piled up and can create a short circuit adjacent to conductors. And so, the electromigration resistance can be increased by mixing the aluminum with the copper. So, we can alloy it with the copper with 0.5%. So, this metallization is deposited either by physical vapor deposition or chemical vapor deposition. Now, the metal selection is done because we have the metal lines. They are the combination of resistors and capacitors, right? So, these metal lines will lead to RC time constant, that how much will be the delay. This delay should be less. So, it is important of the interconnect metallization has been briefly discussed in the earlier introductory section, which is controlling the propagation delay by virtue of the resistance of the interconnection line. This RC time constant of the line varies with the silicon dioxide as a dielectric material, and it follows the equation RC is equal to rho line divided by D line, L square line divided by D oxide, and the permittivity of oxide, where this rho line is the resistivity of the line material, D line is the thickness of line, L line is the length of the line material, and D oxide is the thickness of oxide, and this is the permittivity of oxide. So, depending upon the material which we are using, depending upon that, your RC time constant will be calculated. And while choosing any metal line, there should be some properties, desired properties for the metallization. It should have a low resistivity, easy to form. These metal lines should be easy to form, easy to etch for pattern generation. It should be stable in oxidizing ambient, mechanically stable, it should be mechanically stable, good sticking property should be there, and low stress should be there. Surface should be smooth, stability throughput processing, which include high temperature and dry and wet oxidation. No reaction with the final metal line should be there, and it should not contaminate the device, wafer or the working apparatus. Good device characteristics and lifetime properties should be there. For window contact, low contact resistance, minimum junction penetration and low electromigration is the last desired property. So these are the desired properties of the metallization for any IC. Next is when we do the aluminium metallization, metallization of aluminium is done because aluminium is most widely used metal in the microelectronic industry and particularly for the interconnection and wire bonding. Aluminium is the fourth common conductive element with the resistivity of 2.65 micro ohm centimeter, and the silver has 1.6 micro ohm centimeter. Copper has the resistivity 1.7 micro ohm centimeter. Gold has the resistivity 2.2 micro ohm centimeter. Aluminium can easily dry etch than the other three elements to form the tiny metal lines, tiny metal interconnections. That is why your aluminium is preferred over all rest of the three metal lines. Next is the physical vapor deposition. This physical vapor deposition is one of the process to deposit the metal lines, to have the metal lines, and the most common form of physical vapor deposition are evaporation, E-beam evaporation, plasma spray deposition and sputtering. Evaporation and E-beam evaporation used to be the workhorses in the IC industry, but the sputtering is nowadays very common technique in this microelectronics industry. Sputtering has the advantages like it has the high deposition rate, affordable by modern cathode and target design, the capability to deposit and maintain complex alloy composition, the ability to deposit high temperature and refractory metals, the capability to maintain well controlled uniform deposition on the large 200 mm diameter of wafer, the ability in multi-chamber system, it is easy to clean the contacts before the metallization is done. So these are the some properties why the sputtering is preferred over the physical depositions. So sputtering is usually carried out in a argon plasma by biasing the target negatively, and argon ions are attracted to the target. The momentum of argon ion is transferred to the target, resulting in the ejection of one or more atoms from the surface. Then the sputtered atoms, mostly neutral, fly in the plasma and land on the wafer. Next is the chemical vapor deposition. In case of chemical vapor deposition, it offers several advantages which are excellent step coverage, large throughput, low temperature processing, and the number of metals and metal compounds such as aluminium, copper, tungsten silicide, titanium nitride and tungsten can be deposited by chemical reaction or thermal decomposition of the precursor. The nature of the metal CVD, it is not different from that we have covered in the deposition of silicon or silicon dioxide. So usually the wafer need to be heated at around the temperature 100 degree to 800 degree C to provide the initial thermal energy to overcome the reaction barrier. Then CVD metal can be deposited in plasma. The advantage of plasma deposition is that the energy required to overcome the initial reaction barrier can be supplied by the plasma and the deposition temperature can be decreased. This reduction is especially important for the metal or metal compounds which are used for wires and multi-level interconnections, since their tolerance for the high temperature is limited. Now for the aluminium, we are going to use the chemical vapor deposition. Aluminium can be deposited by several CVD precursors such as triisobutyl Al, which is its chemical formula is C4H93Al. It is also known as TIBA, and it involves the 3 steps reaction. When your TiBa is reacted with hydrogen, it will give you DiBaH. Your DiBaH is the chemical name, which is chemical name from diisobutyl aluminum hydride plus C4H8. This reaction is carried out at 40 degree to 50 degree. See, we have seen that the temperature is very less. Then this DiBaH is reacted with the hydrogen to have the aluminum hydride AlH3 plus C4H8. Then this reaction is processed at 150 degree C to 300 degree C, and finally this AlH3 is processed to have the aluminum metal lines and hydrogen gas as a residual. So in practice, the DiBaH is the chemical precursor decomposing on the wafer surface. However, the direct use of DiBaS, it is not possible in case of, because the processing is done at a very low temperature. So the problem with this CVD aluminum is that if no copper in the material is there, electromigration will be there, electromigration effect will be there. A simple solution is to deposit the 50% of the total thickness of aluminum by CVD and the rest of the sputtering of aluminum copper alloy. Subsequent heating to 250 degree C to 400 degree C allows the copper in the alloy to redistribute in the entire aluminum wiring. This is your aluminum. And alternatively, this CVD aluminum can be deposited with the simultaneously copper doping using the dimethyl aluminum hydride DMAH and cyclopentadienyl copper triethylene phosphine CpCuTeP. So by using these precursors, we can also deposit the aluminum. Next is the vacuum, which is used inside the chambers. For the rough vacuum, we can have the 1 bar to 1 m bar. For the high vacuum, we can have the 10 raised to the power minus 3 to 10 raised to the power minus 6 m bar. For very high vacuum, it may vary up to 10 raised to the power minus 9 m bar. For ultra high vacuum, it should be less than 10 raised to the power minus 9 m bar. So these are the just vacuum levels which we are going to use in the furnace. So next is the vacuum thermal evaporation. In case of vacuum thermal evaporation, it is also known as vacuum deposition, and this is the process where the material used for the coating is thermally vaporized and then it is processed by the potential difference to the substrate with a little or no collision with the gases. So normal vacuum levels are in the range of medium to high range. Okay, so and the another method is the resistive heating technique. The material is heated until the fusion by means of electrical current passing through a filament or metal plate evaporate where the target material is deposited. The evaporated material is then condensed on the surface of the substrate, and the other method of heating is used. We can have the RF coil surrounding by a graphite or BN crucible where the material to be evaporated and fused. So here we have the diagram for the resistive heating evaporation. In case of resistive heating evaporation, it is used to vacuum the pump. Here we have the heater. Then the evaporation will be done because here heating will be provided. This is the target material, and the material will be evaporated and it will be condensed over the substrate surface. And in the second diagram, we have the E-beam evaporation. In case of E-beam evaporation, your beam will be targeted to this target material, and then it will be evaporated and it will be then condensed over the substrate, right? So the method by which we are using the heating, it is just given the name, the resistive heating and the electron beam evaporation. So in case of electron beam evaporation, it is based in the heating produced by a high energy beam bombardment on the material deposit. The electron beam is generated by the electron gun, which uses the thermionic emission of electron produced by the incandescent filament emitted electrons are accelerated by the high voltage potential. A magnetic field is often applied to bend the electrons to the target material. Then electrons can be focalized. It is possible to obtain the localized heating on the material to evaporate with a high density of evaporation power. It allows the controlling the evaporation rate from low to high values to have the best result. Some advantages of this vacuum evaporation is high purity film can be deposited, source of material can be vaporized and may be solid in the form of, so it will be much pure. Deposition rate monitoring can be controlled and it is very much easy. It is least expensive of the PVD process. Some drawbacks: many compounds and alloy composition can only be deposited with much more difficulties. Line of sight and limited area source result in a poor surface coverage. A few processing variables are available for film property control. Source material use may be low. Large volume vacuum chambers are generally required to keep the deposition process in progress. Next, we have the sputtering. The sputtering deposition are the method of the depositing thin film by using the plasma. They involve the ejecting material from target, that is source, onto the substrate such as silicon wafer. Sputtered atoms are ejected from the target and have wide energy distribution, typically in the form of tens of electron volt. And the sputtered ions typically only a small fraction, that is 1% of the ejected particles are ionized and are blastically fly from the target and straight lines, and they will lie go straight and lie on the substrate. The sputtering gas is often an inert gas such as argon or helium. So this is the diagram which is used. This is a furnace which is used for the sputtering. So here we have the pumping system. Some RF source and cables will be used. Water coolants will be there to have to maintain the temperature. This is the target, and this target will be evaporated with the plasma. Some sputtering will be there, and we have this thermocouple. Substrate will be there. When it is evaporated, it will be deposited over the substrate. Some heaters are there so that we can heat up the substrate to cross the barrier reaction. And here also we have the water coolants. So some advantages of this sputtering process: the elements, alloy, compounds can be sputtered and deposited. The sputtering target provide a stable, long-lived vaporization sources. There is a very little radiant heat in the deposition process. The source and substrate can be spaced close together. The sputtering deposition chamber can have a small volume. And some of the drawbacks are: sputtering rates are low as compared to those that can be attained in thermal evaporation. In many configurations, the deposition flux distribution is non-uniform. Sputtering targets are often expensive and the material used may be poor. Most of the energy incidents on the target become heat, which we have to remove for the further process. The last process is the ion beam sputtering. In case of ion beam sputtering, your beam of ion will be projected on a sample and then it will be redistributed. So ion beam sputtering utilizes a ion source to generate a relatively focused ion beam directed at a target to be sputtered. The ion beam consists of a cathode and an anode with a common central axis and applying a very high voltage field of 2 to 10 kilovolt to the anode creates an electrostatic field inside the ion source, which confines the electron around a saddle point in a center of the source. So these are all the deposition processes which are used for the metal line deposition. So in this ion beam sputtering, when argon gas is injected onto the ion source, the high electric field causes the gas to ionize, which create a plasma inside the source region, and the ion are then accelerated from anode region to exit the cathode region, which create a collimated beam, ion beam. The resulting ion beam impinges upon the target material, and via momentum transfer between the ion and the target, this sputter this material onto the sample. So this is all about the ion beam sputtering. So in this lecture we have covered the metallization, how the metallization is done, why the metallization is required, and where the metallization is required. And we have seen the various methods by which we can deposit the metal lines, that is your physical vapor deposition and the chemical vapor deposition. And one example we have seen that with the help of some precursors, how your aluminum can be deposited over the as a metal lines. So thank you so much for today's lecture.